Welcome to my series of lectures on thermodynamics. This is lecture number 13, as I say, lucky for some. In the previous lecture, we had met the second law of thermodynamics, or as the caption here says, laws of thermodynamics. That's not because there are multiple second laws of thermodynamics. After all, there can be only one second law. But there are many different forms in which this law can be expressed. You can see two such forms on your screen right now. In the first form, which is the so-called Kelvin-Planck statement of the second law of thermodynamics, it says that an engine depicted here by Kp bar, an engine which draws a positive amount of heat from a single reservoir and converts that completely into work while working in a cyclic process cannot exist. As we have already said before, this is just equivalent to saying that a complete conversion of work into heat without any other effect, which is an eminently possible process, is actually irreversible. An equivalent statement happens to be the so-called Clausius statement. And that also involves an engine which does not exist, the so-called anti-Clausius engine, whose job it is to actually draw a positive amount of heat Q2 from a reservoir at temperature T2, which is smaller of the two temperatures T1 and T2 shown here, and transfer exactly the same amount of heat to the hotter reservoir. Q1 here is exactly equal to minus Q2, simply because there is no work being supplied either to the system or no work is being done by the system. And of course the system goes in a cycle, so there is no delta U either. Net Q has to be 0 under such a situation, so Q1 and Q2 have to be negatives of each other. What the anti-Clausius engine tries to do is to put a positive amount of heat Q2 from a colder temperature to a reservoir at a higher temperature. This transfer is impossible, and that again is a statement about irreversibility. Transfer of heat from a hotter body to a colder body, that can happen without any other effect, and that happens all the time, is irreversible. We had shown in the previous lecture that these two statements are equivalent. I'm not going to repeat the proof all over again, but basically what you can show is that if you have an anti-Clausius engine and a standard run-of-the-mill Carnot cycle, a reversible engine which runs between two reservoirs, can use it to build an anti-Kelvin-Planck engine. Also, you could show that if you have an anti-Kelvin-Planck engine and a standard run-of-the-mill refrigerator, you can use that to build an anti-Clausius engine. What we will see later is that there are many other different ways of stating the second law of thermodynamics. In fact, we are going to explore quite a few of those different ways of stating the law in these lectures themselves. One of the reasons why the second law has so many different ways of stating it is that depending on what kind of information you want to extract out of it or what kind of situation you want to use it for, different versions of the statement may come in more handy. And we are going to take a look, as I promised, at several of them. But before we can explore those further versions of the second law, we need to take a look at a very simple consequence of the second law as stated, either the Kelvin-Planck or the Clausius statement, which directly involves our friends, the Carnot engines. These are actually theorems which had been discovered by Carnot himself, and they are called Carnot's theorems. The first theorem goes like this. An irreversible engine running between two reservoirs cannot be more efficient than a reversible engine running between them. So that says not only are reversible engines special because they're Carnot engines, but they're actually way special because they give an upper bound on the efficiency possible. You cannot have an engine more efficient than them. In fact, that thing is driven home by the second theorem, which says all reversible engines running between the same pair of reservoirs have exactly the same efficiency. By the way, theorem 1 did not really say an irreversible engine has a lower efficiency. But if you take theorem 1 and theorem 2 together, an immediate corollary of the two would be that an irreversible engine running between two reservoirs has a smaller efficiency than a reversible engine running between the same two reservoirs. The proof of all of these theorems essentially boil down to using the second law. And since the only version of the second law that we have learned so far are the Kelvin-Planck statement or the Clausius statement, what we have to do is to show that if the theorem statements were wrong, we would be able to build, using things that we have, an anti-Kelvin-Planck engine or an anti-Clausius engine. Let's try to see how that proof would go. Now, the technique that we will use to prove theorem 1 is a very familiar one. It's proof by contradiction or reductio ad absurdum. We were supposed to prove that eta I, the efficiency of an irreversible engine, can never exceed that of a reversible engine. So we start by assuming exactly the opposite, that eta I is greater than eta R. For two engines I and R, here I obviously is an irreversible engine running between two reservoirs, and R is a reversible engine running between the same two reservoirs. Of course, that means R is a Carnot engine. Now, these are the two engines in question, and I, the engine, takes in Q1I amount of heat from T1, Q2I amount of heat from T2, and converts Q1I essentially into Wi amount of work, and Wi is given by eta I times Q1I. Remember, Q1I is the heat drawn in by the engine. Q2I is actually negative, so that's actually heat rejected. And Q plus for this engine is actually Q1I. And efficiency times Q plus is exactly what work is. You have something very similar for our reversible engine. Q1R is the amount of heat taken in from the hotter reservoir. Q2R is taken in from the colder reservoir, but remember that's actually a negative amount of heat, so it's really being rejected to the colder reservoir. And the amount of work done, eta R, times Q1R. Efficiency times the heat taken in. Okay, now what we do is we can adjust the scale of the Carnot engine in such a way that the amount of heat it takes from the reservoir temperature T1 is exactly equal to the amount of heat the other engine takes in. So that's what we do now. But one important consequence of doing that here would be that WR, which is eta R Q1R, will also be exactly equal to eta R Q1I and Q1R being chosen to be equal. And eta R Q1I is less than eta I Q1I by supposition. Remember, eta I is a bigger one of the two. And therefore, WR is actually less than WI. That's the real important point here. Now, the next step should be pretty obvious. The moment I say that you are taking in the same amount of heat from the reservoir at temperature T1, from using both of these engines, it should be obvious that I should run one of them in reverse so that the net amount of heat taken in from this reservoir becomes zero and this reservoir returns back to its original state. But notice, among the two engines, the one I'm sure can be reversed is this one. Right? It is a reversible engine by its very definition. So we run that in reverse and leave I running in the same direction as before. In fact, we did call it an irreversible engine, but at this stage we don't really know whether it's irreversible or reversible. The only point is I don't know whether it's reversible. So I'm not even going to try to reverse it. But I can definitely reverse this one. And it will take minus Q2R amount of heat from T2, which is of course now a positive amount, minus Q1R or minus Q1I, which are the same thing from here, and do minus WR amount of work But note that because WR was less than WI, minus WR is a negative amount which is actually bigger than minus WI. Notice what has happened now is that at the end of the cycle, the working substance of I is back to its original state. So is the working substance of R bar, which is this R run in reverse. And the reservoir temperature T1 is also back to its original state because it has gained and lost exactly the same amount of energy to these two engines. As a result, it's back to whatever energy it had and back to the same state as before. And as a result, I can now take I, this engine, R bar, this reversed Carnot engine, and the reservoir temperature T1, all of them together inside a big engine because they are all back to their same state. And what this one engine does is that it takes heat Q2I from T2 and minus Q2R from T2 again here and converts that entirely into work. And how much work? Well, Wi from here minus Wr from here. So Wi minus Wr. But note that minus Wr is actually bigger than minus Wi. So when you add minus Wr to Wi, you get something which is more than Wi minus Wi. That is, you get something which is more than 0. So this particular super engine, which we have built by just putting the irreversible engine or whatever this engine is, and the reversible engine run in reverse, and the reservoir temperature T1, all of them inside my engine, is something which takes heat from a single reservoir and uses it to do a positive amount of work. Once again, I don't really need to calculate and show that this heat taken in Q2I minus Q2R is actually positive. Has to be, because that addition of two heats is exactly what gives me the work done by the overall system. Now, this means that what we have managed to build is an anti-Kelvin Planck engine, something which takes heat from a single reservoir, converts that entirely into work without changing the state of anything else. But this violates the second law. And therefore, the assumption that we have started out with, that eta I is bigger than eta R, must be wrong. Eta I must not be bigger than eta R. So this proves Carnot's first theorem. And what we have used in the process is the Kelvin-Planck statement. Note that because we wanted to use the Kelvin-Planck statement, which essentially involves an engine with only one reservoir, but we had two in our problem, we had to ensure that we can put one of the reservoirs inside the engine. And we did manage to do that. By the way, could have also essentially done this thing by somehow contriving to make the reservoir at temperature T2 lose and gain the same amount of heat by the engine and the reversed engine together, and build an anti-Kelvin Planck engine that way. You should show that actually gives you the same conclusion. Also, you should be able to prove that you can arrive at the same result by ensuring that you will end up violating the Clausius statement of the second law, not the Kelvin-Planck statement like the way we have done here. Anyway, the upshot of all this is we have managed to prove Carnot's first theorem. If you have two engines, one of which can be run in reverse and they are running between the same two reservoirs, then the one which can be run in reverse cannot have a smaller efficiency. Now it's actually rather easy to prove Carnot's second theorem from here. And you don't even have to do any calculation for this. Note that if R1 and R2 are two reversible engines running between the same two reservoirs, then from theorem 1, we are sure that the one which can be run in reverse cannot have a smaller efficiency. Since R1 is reversible, R1 can be run in reverse, eta R1 cannot be less than eta R2. On the other hand, R2 is also reversible. It can also be run in reverse with R1 in the forward direction. And that will immediately convince you that eta R2 Cannot be more than eta R1. Has to be less than or equal to eta R1. And therefore, the only possibility is eta R1 has to be equal to eta R2. That was Carnot's second theorem. What about the corollary? The corollary is actually simple. We have just proven that eta I cannot be bigger than eta R. So that leaves you with two possibilities. Eta I is less than eta R or eta I is equal to eta R. However, if eta I is equal to eta R, then for the same amount of heat taken in from the hot reservoir, both engines would be doing exactly the same amount of work and rejecting the exact same amount of heat to the cold reservoirs. So just run the reversible engine in reverse. That's a reversible engine, you can always run it in reverse. And what will that do? It will take back the same amount of heat from T2 as the engine was putting in, give back the same amount of heat to the temperature T1 that the engine was pulling out, and the work done by one can exactly cancel out the work done by the other. As a result, by running R in reverse, we could undo whatever change happened to the surroundings when I ran. Of course, I is a cycle. Every engine is. So, there was no change in the state of the system in the process, but the surroundings of course changed. But by running R in reverse, we can actually undo all those changes. Which would mean that if eta I were equal to eta R, then the engine we are looking at, the one which we had labeled I tentatively as irreversible, would not be irreversible. After all, this is exactly what we mean by reversible. Something with action on the system and the surroundings can be reversed. And that's exactly what we have just shown. So eta I is equal to eta R is out if I is really irreversible. We already know that eta I cannot be bigger than eta R, so eta I has to be less than eta R. So here we have a justification for the results that we had shown when we were talking about the Carnot cycle. We used three different working substances there, ended up calculating explicitly the efficiency for each of the three cases, and found the same efficiency in the three cases. I mentioned then that that is not an accident. The second law of thermodynamics helps us to prove Carnot's theorem, and Carnot's theorem guarantees that all Carnot cycles running between the same two temperatures will have exactly the same efficiency. And we also see a practical reason why the Carnot cycle is so important. It gives us an upper bound on the efficiency which a real engine can try to get close to, but never exceed. Now, the Carnot theorem actually happens to be a very, very important stepping stone to extremely useful versions of the second law. But even before that, Carnot's theorems guarantee the existence of a special kind of temperature, a temperature which has meaning beyond just thermal equilibrium, something so important that we call it the absolute temperature or the thermodynamic temperature. In order to see where this special kind of temperature comes from, note that what we have said about Carnot's theorems essentially says the following. If you have a reversible cycle running between two reservoirs, the efficiency depends only on the two reservoirs, that is, on their temperatures. And for the time being, I am going to denote the temperatures in any arbitrary scale by theta, because they are still empirical temperatures. And what this tells us is that the efficiency of a Carnot cycle depends only on the two temperatures theta 1 and theta 2. But notice that eta is actually 1 plus Q minus by Q plus. And this tells us that for a Carnot cycle, Q minus by Q plus, the ratio of heats taken in from the colder and the hotter reservoirs, is a function of the two temperatures theta 1 and theta 2 only. In fact, Q minus by Q plus is simply eta minus 1. And that, of course, is a function of theta 1 and theta 2. And let's give it a name. We know that this function is negative. And usually I don't bother changing the sign of something because it's negative. But here, because we already know that Q minus by Q plus has to be negative, we define its magnitude by this function f of theta 1 comma theta 2. So Q minus by Q plus is minus f of theta 1 comma theta 2. Now this result itself, the fact that the ratio of these two heats is a function of the temperatures only, will lead to a thermodynamic temperature notion. How? Basically, Carnot's theorem, which after all is the second law in disguise, will give you a huge restriction on the possible forms of the function f of theta 1 comma theta 2. And in order to see that, we need to talk about a situation where we have a sort of composite engine. You have three reservoirs at temperatures theta 1, theta 2 and theta 3. You are running one Carnot cycle, a reversible cycle, between reservoir 1 and reservoir 2. So this is my first Carnot cycle or reversible cycle R1, and it draws Q1 plus amount of heat from the hot reservoir, Q1 minus amount of heat from the cold reservoir, and does W1 amount of work. The work done here is really not that important for the rest of our discussion here. What is important is that the ratio of these two heats, Q1 minus by Q1 plus, is of course negative of this function f of theta 1 comma theta 2, whatever that function is. We have another Carnot cycle here, another reversible engine R2 running between the reservoirs at temperatures theta 2 and theta 3. And it of course takes in Q2 plus amount of heat from theta 2 and Q2 minus amount of heat from theta 3, and Q2 minus by Q2 plus by the same token turns out to be minus f of theta 2 comma theta 3. So far, this is just from the definition of this Carnot cycle efficiency and a direct consequence of Carnot's theorems, that these results depend only on the temperatures involved. Theta 1 and theta 2 for this ratio and theta 2 and theta 3 for this ratio. Now we are going to do something which you should expect by now. Here you have one cycle and another cycle, two different cycles. Can we put them inside one engine? And more importantly, can I also put the reservoir here inside that engine? With the working substances of the two cycles, there is no problem because they are actually undergoing cycles. So they are back at the original state. But if we want to put this second reservoir inside my engine, I have to ensure that it is also back to its original state. But that is easy enough to do. We already know how to do it. All you have to ensure is Q1 minus plus Q2 plus, which is the net energy released by this reservoir, has to be 0. So the moment you do that, if you choose Q1 minus plus Q2 plus to be 0, then the reservoir in the middle is back to its original state. And that means now we can combine R1, R2 and this reservoir together into a single reversible engine which is running now between two reservoirs, one at temperature theta 1, the other down below at temperature theta 3. Of course, for this what will happen is Q2 minus by Q1 plus, this ratio has to be now given by minus f of theta 1 comma theta 3. Now it's a matter of simple algebra, simple ratios. Q2 minus by Q1 plus, this ratio of course is the same as Q2 minus by Q2 plus times Q1 minus by Q1 plus, but in between you have this ratio sitting in. It's just Q2 plus sitting here, both in the numerator denominator, they cancel, the Q1 minus is cancelled. If you have ensured that you can take the second reservoir inside your engine, that is, if you have ensured that Q2 plus Q1 minus is actually equal to 0, then the ratio Q2 minus by Q1 plus minus f of theta 1 comma theta 3 will simply work out to be minus Q2 minus by Q2 plus times Q1 minus by Q1 plus. These are also heat taken ratios from the two reservoirs of two specific Carnot cycles. And so what you get is minus f of theta 1 comma theta 3. This ratio here is negative, this negative, minus f of theta 2 comma theta 3, that's for Q2 minus by Q2 plus, and minus f of theta 1 comma theta 2 from this one. So the function f is not just an arbitrary function. Carnot's theorem tells us that this ratio has to be a function of the temperatures only. But Carnot's theorem, again used slightly creatively, tells us that this function has to obey this particular restriction. F of theta 1 comma theta 3 has to be the product of f of theta 1 comma theta 2 times f of theta 2 comma theta 3. So Carnot's theorems, and hence the second law of thermodynamics, puts severe constraints in the form of the function f. And the form is very easy to figure out. Well, to begin with, we put all of the three arguments as equal. That is, we put theta 1, theta 2 and theta 3 all equal to theta. So this is f of theta comma theta, and on this side you have the square of f of theta comma theta. So the equation in this special case simply becomes f of theta comma theta is equal to its own square. Therefore, it has to have the value of either 1 or 0. Which one of the two is possible is very easy to figure out from the physics. If you are running a Carnot engine between two reservoirs at the same temperature, its efficiency eta theta comma theta has to be 0. Simply because if the efficiency had not been 0, then you effectively have an engine running with only one reservoir. After all, two reservoirs at the same temperature are effectively only one reservoir, and producing some work out of it, which would definitely be a violation of the Kelvin-Planck statement. Of course, if such an engine had been possible, then the first law would have guaranteed that its efficiency would have been 1. W would have to be equal to Q plus, because here Q plus is the entire Q. And then, of course, F would have been 0. But since the Kelvin-Planck statement forbids such an engine from existence, you must have an eta of 0, that means f of 1. So first of all, one thing we can figure out from this defining equation that you have for f, that if you supply f with two equal arguments, you must get 1. Now, let's choose a special situation here where you put the two temperatures here as equal. Leave theta 1 and theta 2 as different, but theta 1 and theta 1 both are being put equal to each other. What we have just figured out right now is that this left hand side then will have to become 1. So what we get is f of theta 1 comma theta 2 into f of theta 2 comma theta 1 must be equal to 1. In other words, if you switch the two arguments theta 1 and theta 2, the function must become its own reciprocal. Now that's also very easy to understand from a physical point of view. Switching theta 1 and theta 2 essentially means effectively you're running the engine in reverse. Whatever was giving heat before is now taking in heat. Whatever was taking heat away from you is now giving you heat. So Q plus and Q minus change to Q minus prime and Q plus prime with a change of sign. But the ratio, of course, simply becomes a reciprocal. The two minus signs here cancel. So it's very easy to understand why f of theta 2 comma theta 1 is actually 1 over f of theta 1 comma theta 2. Of course, it's a direct consequence of our defining overall equation. Now what we do is the following. Let's choose a fixed value of theta, let's call that theta 0, for the first argument of f. So I will not change that, I will just change the second argument. So of course this now becomes a function of the second argument alone. The first argument is something which we have fixed at some value. So this is how you define a function phi of theta. The important thing is the moment you have defined this function phi of theta, that's enough to figure out what f of theta 1 comma theta 2 is going to be, because f of theta 1 comma theta 2, according to our overarching principle, has to be f of theta 1 comma theta 0 times f of theta 0 comma theta 2, and f of theta 0 comma theta 2 by definition is phi of theta 2. F of theta 1 comma theta 0 is the reciprocal of f of theta 0 comma theta 1, which of course is phi of theta 1. So we see that the function f of theta 1 comma theta 2 must have the form some function phi of theta 2 divided by the same function phi of theta 1. Let's quickly check that this actually is sort of consistent with whatever we have figured out so far. If you put in theta 1 and theta 2 equal, these two phi's will just cancel each other out and you will get 1. So that checks out that f of theta comma theta is 1. And if you were to interchange theta 1 and theta 2 here, it's obvious that here too the same thing will happen. The numerator and denominator will be interchanged and you will be ending up with the reciprocal, which is exactly what we had figured out a while ago. Now, theta was an empirical temperature. That is, its only real job was to specify whether two systems would be in thermal equilibrium or not in thermal equilibrium. We had already mentioned this several times when we were talking about empirical temperatures, that if you change an empirical temperature to a monotone function of that empirical temperature, rather change it in a one-to-one way, then the resulting thing is also a valid temperature. So, notice that this thing is a very important physical quantity, the ratio of the heats taken in from the two reservoirs with up to a minus sign. Can you actually express this in a simple form as temperature of reservoir 2 divided by temperature of reservoir 1 simply by defining phi of theta to be a valid temperature? First thing that you have to check, in fact the only real thing that you need to check, is it 1-to-1? The answer is yes. Because, this is where the maths becomes very directly related to the physics. If phi of theta 2 is equal to phi of theta 1, then f of theta 1 comma theta 2 will have to be 1 and the efficiency eta of theta 1 comma theta 2 has to be 0. Now, with a minute amount of thought, you can figure out that if you had an engine with efficiency 0 running between two different temperatures, that is, theta 1 and theta 2 were different, yet you have a 0 efficiency engine. Remember, this is a reversible engine. Then you will be able to build an anti-Clausius engine. In fact, then you have an anti-Clausius engine. One could argue that such a 0 efficiency engine could take a positive amount of heat from a hot body and deliver an equal amount of heat to the cold reservoir without violating the second law of thermodynamics. And that, of course, would be right. But remember, our engine here is a reversible engine. It's a Carnot engine. So if you have a reversible engine which can do that, then you are actually saying the spontaneous flow of heat from a higher temperature to a lower temperature is reversible, which of course is what the second law tells you is not the case. So, according to the Clausius statement of the second law, if phi of theta 2 is phi of theta 1, the only possibility is theta 2 is actually equal to theta 1. So phi of theta has to be a 1-to-1 function. As a result, it is also an equally valid temperature. In fact, it is very easy to show that this is actually monotone increasing. If theta 1 is greater than theta 2, then f of theta 2 comma theta 1, which is 1 minus eta theta 1 comma theta 2, would turn out to be basically the ratio of the two heats, and that would be less than 1, and therefore phi of theta 1 has to be bigger than phi of theta 2. So not only is this 1-to-1, it's actually monotonically increasing, so it also preserves the basic idea that we have that heat flows from a higher temperature to a lower temperature, not from a lower to a higher temperature. So here, phi of theta is a valid temperature. It is a valid empirical temperature, but now it has an additional thermodynamic significance, which other empirical temperatures don't have. It has a significance that it gives you directly the ratios of the heats taken at two temperatures by a reversible engine running between two reservoirs. And this gives us what is called the absolute temperature scale. We define phi theta to be T. Now notice that in the definition we only got the ratios of phi theta 2 by phi theta 1. And so only ratios of this T have real significance. That's also easy enough to understand. After all, when we defined phi of theta, we chose an arbitrary theta 0 as the first argument of f. and define phi of theta to be f of theta 0 comma theta. It's very easy to figure out that if we were to change theta 0 to say theta 0 prime, the phi of theta will change to another number which is essentially in the same ratio as the original phi thetas. So only the ratio has real significance. Now, going back to the efficiency of the Carnot engine, this formula that Q minus by Q plus is minus T2 by T1 directly gives us that efficiency eta has to be 1 minus T2 by T1 when you are using this new temperature scale, the so-called absolute temperature scale. However, this formula should look very familiar. We had also seen earlier that if you are using the ideal gas temperature scale, then the efficiency eta for a Carnot cycle works out to be 1 minus T2 by T1 in that scale, where T2 and T1 are the ideal gas temperature scales. These two results taken together tells us that the absolute temperature and the ideal gas temperature must bear a constant ratio. They must be proportional to each other. And just by choosing a proper scale, that is a proper unit, we will end up with T equal to T ideal. So the ideal gas scale, which was somewhat special among all empirical gas scales, but only special in the sense that although we defined it using real gases, it ultimately worked out to be independent of the identity of the gas used, turns out to have a much deeper significance. It is actually identical with the absolute thermodynamic scale of temperatures, which has a thermodynamic significance directly in terms of measurable quantities involving heat engines. Why exactly is the ideal gas temperature scale the same as the absolute temperature scale? The answer to that cannot be really understood within thermodynamics. Within thermodynamics, it's just something you discover this way. But if you look at the microscopic picture of temperature as the average kinetic energy, which I'm sure many of you are already familiar with, and take a look at the way in which the ideal gas equation of state is derived, you would be able to see that at a microscopic level, there is a connection between the two. We are not going to really talk about that in this series of lectures in some detail because that would be an entirely different topic. We are really working with classical thermodynamics here. And there what we do find is that at the end of the day, we can define a temperature scale with thermodynamic significance, which happens to coincide with the proper choice of units with the ideal gas temperature scale. Now that we have this temperature scale, we will find that there is a very, very special role which this T plays as an integrating factor for an inexact differential. This will ultimately lead us to the notion of a very important thermodynamic quantity, the so-called entropy. But before we go to entropy, we must go through something called Clausius inequality. That will be the topic of our next lecture. Bye for today.